trace the long arc of our species, and you keep arriving at the same restless instinct hidden beneath everything else. The need to see what lies past the next ridge. The pull toward whatever sits just beyond the edge of the visible. We came into this world without the gifts that kept other creatures alive. No great strength, no natural weapons, no armor, no speed. What we carried instead was a mind that refused to accept the edge of the map as the edge of what was possible. We pictured places we had never stood in, and then we found ways to stand in them. That single trait, more than any other, is why a small and breakable animal came to spread across an entire planet and then begin reaching past it. But every hunger eventually meets a wall. Every clever answer runs sooner or later into a problem that refuses to bend. So the question worth sitting with is not how far we have already traveled, because that version of the story is built to flatter us. The harder question is where the road actually ends. How far can imagination and engineering carry a species before physics quietly closes the door in front of it? It may be uncomfortable to consider, but there is a real chance that we are already standing close to that door, that we have spent decades mistaking the size of our own backyard for the size of the cosmos, and that the gap between the two is far wider than our pride wants to admit. There is a real and earned pride in looking back at what we have accomplished beyond the atmosphere. In an astonishingly short span of time, we went from never having left the ground to placing human footprints on another world. We learned to build machines that could tear free of gravity, survive the airless dark, and keep working millions of kilometers from the nearest human hand. That is not a small thing, but it is a much smaller thing than it feels like from the inside. Our robotic explorers tell the truth more honestly than our memories do. Voyager 1, sent out in the late 1970s, is still moving away from us right now, and it has already slipped past the heliosphere, the vast bubble carved out by the solar wind. It is the most distant object human hands have ever made, and yet, after nearly half a century of unbroken travel, it has not come remotely close to another star. That single fact is the entire scale of the problem compressed into one wandering machine. In terms of pure engineering, we have grown genuinely capable. We have landed rovers on Mars with the precision of a careful parking job. We have placed spacecraft into orbit around Jupiter and Saturn, photographed frozen worlds at the cold outer rim of the solar system, and even flown a small helicopter through the thin air of another planet. Missions carrying names like Cassini, Juno, New Horizons, and Perseverance proved that we can send delicate hardware across enormous gulfs, gather real data, and keep a conversation going across years of distance. We have even reached remarkable speeds. The Parker Solar Probe, diving in toward the Sun, has been clocked at more than 600,000 kilometers per hour, a velocity unthinkable on Earth, and still almost nothing against the distances between stars. Here is the quiet truth underneath every triumph. Every machine we have ever launched has stayed inside the same gravitational bubble. We have thrown our hardware farther and farther, but always within the reach of one ordinary star. We are extraordinarily good at moving around our own house. We have never once stepped outside it. The moment we begin talking seriously about traveling to another star, the trouble appears before technology even enters the conversation. The first obstacle is not the engine or the fuel. It is the distance itself, and it is a distance the human mind is simply not built to feel. The solar system seems vast when you think about Mars, or Jupiter, or the long fall out to Saturn, but all of that is packed in close when you compare it to the emptiness between the stars. Proxima Centauri, the nearest star to our own, sits roughly 4.25 light years away, around 40 trillion kilometers. It is a number so large that it stops carrying any real meaning. The mind reads it and slides right off. So try a more practical way of feeling it. Imagine sending a craft outward at the speed Voyager travels, somewhere near 17 kilometers every second. At that pace, a journey to the nearest star would take something on the order of 70,000 years, longer than the whole of recorded civilization. Longer than writing, longer than agriculture. A ship launched at the dawn of human history, moving the entire time, would only now be approaching the closest neighbor we have. and even our fastest machines barely improve the picture. The Parker Solar Probe, with its record-shattering speed, would still need thousands of years to span just a few light years, in a perfect straight line, with no slowing down and no obstacles in the way. These distances are not unlucky exceptions. Most nearby stars sit at comparable removes, scattered between 5 and 20 light-years out, and the numbers grow violently as the view widens. Our galaxy stretches roughly 100,000 light-years from edge to edge. There is a reason for all of this, and it is worth saying plainly. The space between stars is not just large, it is mostly nothing. Each star is a tiny lit island, floating in an ocean of near-perfect emptiness, and the islands are absurdly far apart. When you set the distance from the Earth to the Sun beside the distance to the nearest star, the gap between them is something like 250,000 times over. Reaching another star is not a longer version of a trip we have already taken. It is a completely different category of journey, on a completely different order of scale. Once the size of the distance settles in, the next wall rises immediately behind it. We do not possess, and have never possessed, any method of propulsion capable of moving us fast enough to make the crossing in any reasonable amount of time. Nearly every spacecraft we have ever flown runs on chemical propulsion, the same idea that lifted the first rockets at the start of the space age. You burn fuel, you hurl gas out the back at high speed, and the reaction pushes you forward. It works beautifully for escaping Earth's gravity and maneuvering within the solar system, but it carries a built-in trap. The faster you want to go, the more fuel you must carry, and the more fuel you carry, the heavier the ship becomes, which means you need still more fuel to move that added weight. At some point, the whole arrangement collapses under its own logic. For the distances between stars, this is simply a dead end. Ion propulsion does better, using electricity to fling charged particles outward for a gentle, continuous push that can run for years on a tiny supply of propellant. But the thrust it generates is almost laughably small, a force you could measure against the weight of a sheet of paper. Even running for years, it accelerates far too slowly to reach the speed an interstellar journey would demand within several lifetimes. Then there are the bolder ideas, the ones that live mostly on paper: nuclear fusion engines, drives that feed on antimatter, enormous light sails pushed by ground-based lasers. Each is genuinely promising on the page and collides with an unanswered obstacle in reality. We have not mastered fusion even here on Earth, let alone shrunk it into a reactor small enough to ride aboard a ship. Antimatter engines fail before they begin, because we have no way to manufacture antimatter in any amount that would matter. The laser-driven sail, the centerpiece of concepts like breakthrough starshot, would demand staggeringly powerful lasers and a sprawling planetary infrastructure. And, most damning of all, it offers no realistic way to slow the ship down once it arrives. In every case, the same pattern repeats. Each gain in speed requires a wildly disproportionate jump in energy, and we have no way to produce or store energy at anything close to those levels. Suppose we solved all of it. Imagine an engine vastly superior to anything we have today, one that could pour out thrust without limit. Even then, a barrier waits that no engineering can defeat, because it is not a problem of technology. It is woven into the structure of reality itself. It is the speed of light. The relativity Einstein laid out more than a century ago is unambiguous. Nothing that carries mass can ever reach the speed of light through empty space, let alone exceed it. When you push any object faster, part of the energy you spend does not go into velocity at all. It goes into increasing the object's effective mass. The faster it moves, the more massive it behaves, and the more energy it then takes to keep accelerating. The demand does not rise steadily. It snowballs towards something impossible. As the velocity creeps toward the full speed of light, the arithmetic simply detonates. To actually reach that speed, you would need an infinite supply of energy. Another way of saying the universe forbids it outright. And here is the part that should genuinely humble us. Imagine that, against all reason, we did it. We reached that ultimate speed. The nearest star would still lie more than 4 light years away, which means that even at the fastest velocity the universe allows anything to travel, the journey to our closest neighbor would still take years. The cosmos does not just make the trip hard. It sets a hard ceiling on how fast the trip can ever be made, and then places the nearest destination far beyond what even that ceiling can comfortably reach. When we picture a voyage to another star, we tend to imagine a clean straight line between two fixed points. But near the speed of light, both time and motion begin to behave in ways that make even the act of aiming almost impossible. Start with time itself. One of relativity's stranger and fully real predictions is that the faster a ship moves, the more slowly time passes for everyone aboard it. A ship traveling at 95% of light speed toward a destination 10 light years away would take roughly 10 years to arrive as measured on Earth, but for the crew inside, only about 3 years would pass. Push the velocity higher and the gap widens dramatically. At the most extreme speeds, a handful of years for the travelers could correspond to centuries unfolding in the world they left. It sounds like a loophole, and it is not. Reaching those velocities demands energy far past anything we could assemble. The journey still consumes centuries in the outside frame, and the slowing of the crew's clocks changes nothing about the radiation, impacts, and where the ship must survive along the way. The next complication comes from the stars themselves. The universe does not hold still. The light reaching us from any star shows us where it sat years or decades ago, not where it is now. Every destination is in constant motion, drifting as it circles the galactic center, just as we are. Traveling to a star is not a matter of pointing at the light you can see. It is a matter of predicting where the target will actually be by the time you arrive. Over decades and centuries, even the tiniest uncertainty in that prediction grows into an enormous error, and the target slides far from where you expected. You would need navigation able to correct course continuously, sensors of staggering precision, and predictive models that stay trustworthy for lifetimes. We have nothing remotely like that. Even our finest star catalogues accumulate errors with the years, and after a few centuries, the predicted position of a star can drift far enough to make any interception hopeless. The ship ends up sailing toward a place where its destination used to be, chasing a moving target across an ocean, using maps already out of date with no way to ask for directions along the way. We like to imagine the space between stars as a flawless vacuum, a perfect nothing. It is not, and that small correction turns out to be lethal. Even in the cleanest stretches of the galaxy, there are scattered things, lone atoms, simple molecules, microscopic grains of dust, and now and then a tiny chip of rock or ice. At slow speeds, none of this matters. At relativistic speeds, every one of those specks becomes a weapon. The average density of matter out there is genuinely low. In many regions, you might find only a single atom in each cubic centimeter of space. That sounds like nothing, and it would be nothing if we were drifting at the gentle pace of our current probes. But as speed climbs, the energy of every collision climbs with it. At 1/10 the speed of light, a single mote of dust striking the ship could release energy comparable to a rifle round, pushed toward 1/2 or 9/10 of light speed, and particles no bigger than grains of sand carry the punch of high explosives. Even lone atoms slamming into the hull would generate bursts of ionizing radiation and could bore surprising distances into solid material. The danger sharpens further in regions where matter gathers more thickly, drifting clouds of gas, lanes of interstellar dust. A ship moving fast enough to make the journey short could not pass through an environment like that without catastrophic damage. A thin wisp of gas, utterly harmless at ordinary speeds, could shred a spacecraft moving at a meaningful fraction of light speed. This problem alone would require shielding we have no idea how to build, able to withstand a ceaseless barrage of fiercely energetic impacts. It is a factor that almost never appears in the dreamy conversations about reaching the stars, and it adds directly to the wall of speed. The faster you try to go, the more savage the road becomes. Past a certain velocity, the gap between stars stops being an empty corridor and turns into a continuous storm of impacts. Imagine that every technical wall fell. Energy, speed, navigation, shielding, all solved. There would still remain the oldest problem of all, keeping human beings alive, healthy, and able to function across a journey measured in decades or longer. The body, unlike the machine, cannot be redesigned at will. The first threat is radiation from deep space. Once you leave the shelter of Earth's magnetic field, the levels rise steeply, already a serious worry for a trip to Mars, and far worse on an interstellar voyage. High-energy cosmic rays slice through ordinary materials with ease, damaging DNA, raising the risk of cancer, disturbing the nervous system, and corrupting the very electronics meant to keep everyone alive. Then comes the slow erosion of the body in low gravity, where muscle wastes away and bone loses density at an alarming rate. Even on missions lasting only months, astronauts must exercise hard every single day just to hold the decline at bay. Stretch that across decades, and even the most disciplined countermeasures would struggle. The mind suffers too, and that may be the harder problem. Our current missions already show that long stretches of isolation, confinement, and limited contact wear heavily on mental health. Picture a crew sealed inside a single vessel for years, cut off from any direct word with Earth, locked into a relentlessly repetitive routine. Long-duration simulations that confined crews for well over a year revealed how this kind of isolation breeds chronic stress, disrupted sleep, and friction between people forced to share the same small space. The communication gap only deepens it. Even at Mars, a message can take tens of minutes, while across interstellar distance, a single transmission might take years to arrive and years more to return. The crew would be utterly alone, forced to make every critical decision themselves, the ship running as a fully self-governing world because mission control would, in any practical sense, be gone. Beneath all of it runs the simple fact of the human lifespan. Even if a journey could somehow be completed within decades, the crew would still age across it. And for the truly long voyages, you arrive at the troubling idea of generation ships, vessels where people are born, live, and die in transit, where children inherit a mission they never chose and spend their entire existence within metal walls, bound for a destination they will never see. The machinery may evolve. The body still answers to the rules of biology, and those rules do not care how badly we want to leave. When the obstacles start to look insurmountable, the imagination does what it always does. It reaches for ways around the problem instead of through it. Ships where whole generations would live and die before arrival. Crews put to sleep for the duration. Shortcuts folded through space. Engines that bend space around the vessel. Each is fascinating, and each, examined closely, simply trades one impossible problem for another. The generation ship is usually the most grounded of these dreams. Rather than finishing the trip within a single human life, you spread it across many. The mission departs with one crew, continues with their descendants, and concludes with people who have never touched the Earth. It sidesteps travel time, but opens a host of other problems. Such a ship would have to operate flawlessly for centuries, without a single catastrophic failure, sustaining agriculture, recycling its air and water, and somehow holding a society together. And there is no guarantee that a community sealed away for that long would keep its cohesion, or even remember why the voyage began. Hibernation tries to dodge those social dangers. If the crew could sleep through the decades, the demand on resources would shrink, and the journey would grow far simpler. But nothing of the kind exists. We have no technology that can safely suspend human metabolism for that long, and no life support reliable enough to run for decades without anyone awake to fix it. And even asleep, the crew would still face radiation, impacts, and mechanical failure while lying helpless. When those options falter, the conversation turns to the truly exotic: wormholes and warp drives. Wormholes appear constantly in fiction as instant doorways across space, and they do emerge from certain mathematical solutions within general relativity. But there is no evidence they can exist as stable, traversable structures, and they would demand forms of matter with negative energy density, something never once observed in nature. Even if one could exist, you are left with the obvious questions. Where exactly does it lead, and how do you know the far side is survivable, or that the tunnel will hold together while you pass through? Which brings us to the warp drive, the idea first sketched in the 1990s, of deforming space-time around the ship rather than moving the ship through space. The concept is to contract space in front of the vessel and stretch it out behind, riding inside a bubble so that, locally, the ship never breaks the speed of light. It is space itself that moves. On paper, this could shrink a crossing of several light years down to months. But once you leave the page, the problems are arguably worse than anything before. When you fire up a warp bubble and leap, you arrive long before any fresh light from your destination could reach you, flying toward a target without truly knowing where it is, while the star may have shifted, changed, or passed through some violent event you cannot see. Navigation becomes blind because nothing outside the bubble can be reliably observed during the journey. Every calculation has to be locked in beforehand, accounting for centuries of stellar motion with flawless accuracy. The models even suggest that dust and debris would be swept up and compressed ahead of the ship, then released as a blast of high-energy radiation when the bubble collapses, a danger to the vessel and to whatever waits at the destination. And underneath it all sit the theoretical demands: exotic matter we have never found, and energy in quantities that dwarf anything our civilization could ever generate. In the end, none of these escapes actually escape. The grounded ones break against biology and the impossibility of running a sealed world for centuries. The exotic ones rest on physics we cannot confirm is even real. Every one of these ideas was born because the distances are too vast for the tools we have, and everyone creates a problem as large as the one it set out to solve. Perhaps the greatest barrier standing between us and the stars is not written into physics at all. Not in the engines, not in the distances, not in the merciless arithmetic of relativity. Perhaps the real limit is us. Consider the strange contradiction we live inside. We command rockets and understand the deepest laws of motion. We detect planets circling stars we will never visit. We model entire universes inside our machines. And at the very same time, we remain a species fractured against itself, divided by lines that seem impossible to erase. In politics, in economies, in the way we treat the world that sustains us, we so often pull in opposite directions at once. We are a single species that behaves as though it were many, competing for the same ground instead of sharing it. And here is the uncomfortable truth at the center of it. No undertaking large enough to carry us beyond the solar system could ever be built without cooperation on a global scale. A project like that does not belong to a single nation, or an economic bloc, or an ideology. It would require something we may never have truly managed, a humanity that acts as a humanity. It is entirely possible that long before we reach the point where physics becomes the obstacle, our own civilization will have already tripped over its own feet. Maybe the unity such an effort would demand simply never arrives. Or maybe we reach the threshold too late, after our resources, our climate, or our own stability have quietly stolen the chance away. And that is the part that lingers longest. It is not certain that the universe is what keeps us pinned to this single point of light. It may be that we are doing it to ourselves. The final wall may not stand out among the distant stars. It may stand right here in our own inability to act as one species before the time to try has finally run out.